Okay. Good morning, everybody. Um, Thank you, Corey. Thank you, Ronald, Fox. Thank you, Ernesto. All right, I was talking about new topic in complex analysis. And yesterday, I started uh, talking about sequences and series. And I also, by the way, gave you a review problem so that you can work on those to sort of sharpen your skills in dealing with um, sequences and series. So why do we need those review problems? Why do we need to sharpen our skills uh, in sequences and series that you learned in calculus? Here is why. When it comes to um, sequences, when it comes to sequences, a sequence in complex looks like this, right? It has a real part and also an imaginary part. And we notice that if you want to take limit of a sequence, and that's always the case, as soon as you have a sequence, you want to know how that sequence behaves when n gets extremely huge. We notice that limit of Zn, the sequence, is the same as limit of its real part plus I, limit of its imaginary part. But when it comes to limit of real part and imaginary part, these are calculus 2. That is why you need to review calculus. Now, after sequences, certainly, naturally, we want to talk about series. And we notice that a series of complex numbers, which is the n, of course, is xn plus I'm real part plus I imaginary part, is the same as saying that the series of the real part plus I, the series of imaginary part, all right? So this is the reason, because when you want to find the infinite summation of complex numbers, it goes to its series of real parts and series of the imaginary parts, right? So these are the series from calculus 2. That's why we need to um, review those. Now, something very interesting here, um, and that is when uh, you take modulus of Zn, right? And the series converges. So if you take the modulus, if this series converges we say this original series converges absolutely, all right? We say this series converges absolutely. Now, what happens if a series converges absolutely? Oh, look, if this guy converges, but this Zn is actually the modulus, which is the square root of xn, the real part squared plus imaginary part squared, is bigger than or equal to just the real part, absolute value of real part, or absolute value of the imaginary part, right? Well, if the series taking modulus converges by comparison test, these two series will converge absolutely, all right? So if this is a beautiful observation, if this series converges, so does the series of real part, maybe it's so do these two. Therefore, these two series converges absolutely means they will converge, okay? So that's why we are really interested in taking modulus. And the first thing we would like to do always is take modulus and see if the series converges, because as soon as this one converges, we know that these two will converge. As a result, the original series will converge, okay? So always we are going to work on this one. And when you take modulus, now there is no complex number involved. It is just this one, right? Which is a real number. So we can go ahead, go to the calculus 2 and apply those tests to this guy. And that's what we call generalized ratio test or generalized nth root test, okay? Okay, here is what we do. So the first thing we do, we would like to see if this guy converges. And now this is a real sequence. So that is what we apply generalized, okay? Let me say generalized ratio test. Or nth root test. What is generalized ratio test? Well, you will consider the ratio of these. So you will take the ratio of Zn plus 1 over Zn modulus. And suppose the limit exists and is L. If the limit is L, several things can happen, of course. That L can be less than 1. If it is less than 1, this series converges absolutely, all right? Converges absolutely. If it is bigger than 1, the series diverges. Okay? And L equal 1, no conclusion. If it is 1, no conclusion or inconclusive. All right. So, this, by the way, generalized ratio, this is extremely powerful, and we will use it all the time. So, okay. Any questions so far? Just giving you the idea why you need to go back to Calculus 2 and review our sequences and series facts, okay? Now, among this different series, we are really interested in this type of series, which are called power series. If it is in the form of powers of z minus z naught is called the center. Power series center that z naught, all right? And z naught is fixed, and this is also fixed. The question is, for what values of z this series is going to converge? Well, that's the main thing. Okay. Here are a few examples. See, z naught is 1 plus I. Here is a power series centered at 1 plus I. And this AK, this sequence, is right here. Okay, it's right there. So the question is, look, for what values of z this will give us a convergent series? Well, always that generalized ratio test is going to help us. Think about the whole thing as BK. So you will form BK plus 1 over BK modulus, all right, modulus. As I said, this generalized ratio test is extremely powerful, and we will always use it. So here is BK plus 1 divided by bk. Divided by bk means you multiply by reciprocal of bk. You do a bunch of cancellation, right? After those cancellations, this is what we get. And you take limit as k approaches infinity, right? Usually we use bn and n approaches infinity, but numerator is a constant after getting z. This is a constant. If denominator, you have k. As k approaches infinity, this becomes 0. So going back to this generalized ratio test here, when you take limit and limit exists, if the limit is less than 1, the series converges absolutely. So here, the limit is 0. When the limit is 0, that is your L, is less than 1. So the series converges absolutely. No matter what Z, always converges, all right? Always converges. So this is a good example for power series. As I said, given a power series, we would like to know for what values of Z the series converges. And this particular one, this particular example right here, doesn't matter what Z is, always converges absolutely. All right, converges absolutely. Okay, let's have another example. Here's another example. If I let this Z be 0, all right, it converges to 1. But what if Z is not 0? Well, look, if Z is not 0 and you apply that generalized ratio test, here is generalized ratio test. Call this one a sub k or whatever, a sub k plus 1 over. So you need to form a sub k plus 1 divided by a sub k, modulus of that, of course. So in numerator, I'm going to have k plus 1 factorial z to the k plus 1, that is a sub k plus, divided by, in denominator, I will have k factorial modulus of z to the k. What is the result? The result, k factorial and k plus 1 factorial will give you k plus 1. And here modulus of z. I already talked about the case when z is 0. But when z is not 0, this is the positive quantity. And as k approaches infinity, this is going to be infinity, right? So in this case, limit of ak plus 1 divided by ak as when z is not 0, right? As k approaches infinity, is infinity. This is your L. This is the L, which is bigger than 1. So the series diverges. The only time that the series converges is for z equals 0. Otherwise, it diverges. All right. This is another example. Here is, oh, yeah. So the series diverges. That was example number 2. Here's another example. Example number 3. Let's look at this series. For different z, you are going to have different series, right? And as a result, the question is, for what values of z this series will converge? Well, we use generalized ratio test. Here is the ratio. Here is a sub k plus 1 multiplied by reciprocal of a sub k. After simplification, this is what you get. Now, we need to take limit of this guy as k approaches infinity. As k approaches infinity, this limit is 1. And you will end up with z. So, using that generalized ratio test, this is the limit. If this is less than 1, this is your L. If this is less than 1, the series converges with this series right there, series of example 3. And if this is bigger than 1, it diverges, and equal 1, that's another story. So if modulus of z is less than 1, the series converges absolutely. What does it mean? Oh, here are the points where modulus of z on the circle, modulus of z is 1. Inside the circle, modulus of z is less than 1. Outside is bigger than 1, all right? So this is giving us the circle or this disk. For points inside the disk, the series converges absolutely. Outside diverges. On the circle is a little bit tricky. For the time being, we just would like to stay inside the circle. Then the modulus of z is less than 1. Okay. Now this sort of calls for a couple of terms. This radius of this circle is called radius of convergency. And this disk is disk of convergence. Okay. For any Z you choose in here, that series converges. And we like this one, right? We like this one. Radius of convergence. Okay. Here's another example. See, this is a series, power series, centered at 2i. The question is, for what values of z this is going to converge? This infinite summation is going to give us a number. If we use that generalized ratio test, you will get this one. The limit is this guy. So this is your L. If L is less than 1, the series will converge absolutely, all right? And that means here is the disk of convergence. And radius of convergence is 1 again, all right? So it is a disk centered at 2i with radius 1. Okay. So one of the basic problems in this topic is given a power series, find the radius of convergence. Okay, that radius of convergence can be a number, here 1, can be infinity, which means the series converges everywhere. That example number 1. Or that radius of convergence can be 0. Example number 2. All right, example number 2. Okay. Any comment, any questions so far? All right, I don't see any question. So I will continue this topic of dealing with power series. Here is example number 4. I'm giving you a bunch of examples. Hopefully, you will get the idea. Of course, you saw similar things in calculus 2. In calculus 2 also, you saw power series, and you wanted to find the radius of convergence there. Now, look at this one. It's an infinite summation. I just wrote a few terms. When n is 0, you get 1. N is 1, you get z cubed divided by 4. N is 2, you get this, and so forth. It's an infinite summation. The question is, for what values of z this series converges? And the tool that we will use to answer this question would be the generalized ratio test, okay? So think about this as an and form the ratio of an plus 1 over an. And usually you will have a bunch of simplification, right? Here you have when an plus 1, oh, be careful. That means replace n by n plus 1. If you replace n by n plus 1, it will be 3 times n plus 1, right? Quantity n plus 1. So this is it divided by 4 to the n plus 1. Multiplied by reciprocal of an. Here's reciprocal of an. Well, this cancels. Here you get z cubed, and here you get 4. Now, when you take limit as n approaches infinity, this is the limit. By generalized ratio test, if this is less than 1, the original series converges absolutely, all right? So this has got to be less than 1, which means z cubed is less than 4 multiplied by 4. So z has to be less than third root of 4. And this is the radius of convergency, okay? That is the radius of convergency. So in this case, the center of the power series is 0. So it will be a circle of centered at 0. Here is 0. X-axis, y-axis. And the radius, this much, is a third root of 4. So if you stay within this disk of convergency, the original series converges absolutely. If you go outside, it diverges, right? So this is the disk of convergency. Radius of convergency is right here, third root of 4. Any comment, any question? So as you see, our tool, the main tool to find the radius of convergency would be the ratio test, the generalized ratio test, all right? Okay. So enough examples of power series, but here is why we like power series. Here's why we like power series. See, when we deal with polynomial, a polynomial of degree n looks like this. The degree of this polynomial, the highest degree, is n, assuming that Cn is not 0. Cn is a coefficient. These are called coefficients, C0, C1. Here's a polynomial of degree n. When we are dealing with a polynomial, differentiation is easy. Taking derivative is easy. How do we take derivative? Just we take derivative term by term, right? We integrate term by term. But there is a difference between a polynomial when you have finite number of terms. It could be 100 terms, that's fine. Still, it is a polynomial. There is a difference between a polynomial and an infinite series. This is an infinite series. This series, this polynomial makes sense for all z's. But here, For certain z, this might diverge. We don't like this to diverge and give us infinity. For this one, we need to work in its disk of convergency, all right? Now, interesting enough, this power series behaves like a polynomial inside its disk of convergency or circle of convergency. What do I mean by behaves like a polynomial? Its derivative will be derivative of these terms. Its integral will be integral of these terms, all right? So, and of course, it's inside the disk of convergency, it will be continuous, all right? Okay. So it is continuous. Derivative is term by term exist. If this is the power series, its derivative, just you go ahead and take derivative of each term. So you differentiate term by term, and you integrate term by term, all right? You integrate term by term. This is what I meant by power series. In a way, behave like polynomials. It's a generalization of polynomials. But remember, inside its circle of convergency, all right? Inside. All right. So a lot of functions do not look like polynomials, right? So here is derivative. Suppose this is has radius of convergence r. Its derivative, you take term by term derivative, all right? You get this. How about radius of convergency of this derivative? Well, let's apply the generalized ratio test. This time, this is the series. This is a sub n. So you form a sub n plus 1 over a sub n, you get this. Now, as n approaches infinity, limit of this guy is 1. All right? And limit of this guy is the same as this one, all right? This will be radius of convergency. And if we call it r, then that's whenever this is less than 1, you know, it converges and so forth. So limit of this guy is r. As a result, oh, this is the reciprocal of Cn over Cn plus 1. And by generalized ratio test, this one has the same radius of convergency as the original series, okay? So, when you have a power series, with radius of convergence being r, its derivative, if you take derivative term by term, that one also has radius of convergence, the same radius of convergence. Okay, its integral also have the same radius of convergence. That's good to know. That's good to know. Okay, that's a very beautiful fact. So one of our goal is given a function. See, this is not a power series, right? But the question is, since we like power series and they behave like sort of polynomials, can we write the power series representation of this function? Here's another function. Here's another one. Can we write sort of a power series representation of these functions? Well, we have a theorem called Taylor's theorem, and that Taylor's theorem, although I'm not going to prove it for you, just going to mention it, what that Taylor series is. Here is the Taylor series of a function. If the function be analytic, the Taylor series centered at alpha. This is f of alpha, f prime alpha, f double prime alpha over 2 factorial, and so forth. The general term is the kth derivative of f evaluated at alpha divided by k factorial times z minus alpha to the k, all right? This is alpha, this center. This is called Taylor series of the function with center alpha. Of course, the main question is this series, right on the right-hand side, this series, a convergence series? And if it converges, is the value of this series the same as f of z for different z's? And that is Taylor series, that theorem is about, right, Taylor series theorem. As I said, I'm not going to prove it, but those of you who are interested in looking at the proofs, please go ahead and look at the proofs. And if you have any question about the proof, just ask me, please. Ask me, please. I'd be more than happy to go through all the details of that theorem. So here's a theorem. So this is Taylor series of the function centered at alpha. But sometimes alpha is 0. So here we get z to the n, and we evaluate the nth derivative at 0. This is called Maclaurin series. It is the same thing, but, well, different names. Taylor series centered at alpha, Maclaurin series. So from this point on, since we like power series, given a function, we will try to find a power series representing that function, all right? Power series, either Taylor series or Maclaurin series, just a power series representing the function. And this Z is a little bit funny. Okay, example. I'll look at f of z equals e to the z. I want to find the Maclaurin series of this function. I want to find this series right here. What I need here is nth derivative of the function evaluated as 0. Here is the nth derivative. Derivative of e to the z is always e to the z. And when you evaluate at 0, let z be 0. E to the 0 is 1. So after finding the nth derivative evaluated at 1, it's Maclaurin series. Remember, this is Maclaurin series. The nth derivative of e to the z evaluated at 0 is 1. So here you get 1. N factorial, z to the n. That's it. This is the Maclaurin series of e to the z. Right? So this is one of the things that we will do. Given a function, we would like to find its Taylor series or Maclaurin series. If we go through the same process, here is for cosine z. This is the Maclaurin series of cosine z. And here is for sine z. Okay, is for sine z. Well, I'm sort of getting you a lot of material. Let me see. Based on today, today I was supposed to talk about, today is 22nd. So, oh, I was supposed to just cover 15.2. And 15.2, yeah, just checking your book, although I got so excited about the topic that I went a lot further, I believe. Yeah, 15.2 is just power series. And 15.3 is other material that I will cover next time, all right? I will cover next time. And Taylor series is 15.4. So I will stop at this point. If you have any question or comment, please go ahead and ask me right now. So although I went ahead and talked about Taylor series, but tell you what, just go ahead and concentrate on 15.1 and 2, and those review problems, and the homework problem will be 15.1 and 15.2. Any comment, any question? I don't see any question. Then um, oh yes, I have received your email. I'm going to check and see what happened. I'll let you know during the weekend. I will verify that one. Any other comment or question? Okay. If there is no question, have a good day, everybody.